morning, sir.
Good morning.
So a very good morning to all the faculty members, our eminent speaker, Dr. Anirudh Chandra, and dear participants. I welcome you all on day 3 of session 1, session 1 of AICTE ISTE 1 week online refresher program on artificial intelligence in cooperative Noma 5G network. I would like to welcome our eminent speaker, Dr. Anirudh Chandra, Associate Professor from NIT Durgapur. It's my pleasure to introduce him. Dr. Anirudh Chandra received BE, MBA and PhD degrees from Yadav University, Kolkata in 2003, 2005 and 2011 respectively. He joined the Electronics and Communication Engineering Department, National Institute of Technology, Durgapur in 2005. He is currently serving as an associate professor there. In 2011, he was a visiting lecturer at the Asian Institute of Technology, Bangkok. From 2014 to 16, he worked as a Marie Curie Fellow at Brno University of Technology, Czech Republic. He has published more than 100 research papers in referred journals and peer-reviewed conferences. He is a co-recipient of the Best Short Paper Award at IEEE VNC 2014 held in Paderborn, Germany, and delivered a keynote lecture in IEEE MNC App 2012 held in Bangalore, India. Since 2020, he is working as a secretary of the IEEE P2982 Standard Working Groups. His primary area of research is physical layer issues in wireless communication. He has published more than 45 journal papers, 70 conference papers, 2 books and 2 book chapters. He has organized many workshops to students, faculties and research scholars, and also organized many national conferences and international conferences. He is a PI, co-PI coordinator for the external projects. He has delivered many talks, tutorials, and conducted faculty development programs. His research interests are millimetre wave for 5G, vehicular communication, free space optical communication, etc. I welcome you, sir. And now I would like to invite Dr. Anirudh Chandra to deliver his talk on cache-aided NOMA networks.
Thank you, Dr. Dhingra, for the nice introduction. So welcome all and good morning. Today my topic is cache-aided NOMA networks, and as you can see, that has been a series of nice, interesting talks on NOMA. So my topic is also aligned to that. However, I will be talking a bit a particular aspect of NOMA, which is cache-aided. So I will share my presentation now and we'll begin.
Namaskaram sir, Vishnu sir. అరే సార్ ఉదయం ఫస్ట్ అవర్ క్లాస్ ఏం ఫాస్ట్గా వచ్చాము మీరు కనపడలా అయిపోయాక టీకి వెళ్ళాం
నేను చూసాను సార్ మీ టీ నుంచి రావడం చూసాను సార్.
Yes, all participants are requested to mute your microphone.
రాకుండా అయినా నీతో పాటు పిహెచ్డీ చేసిన పై
రెండో అటానమస్ లేగా ఇప్పుడు.
హలో
Can you see my slides, Professor Mathur and Dr. Dhingra?
Yes, sir.
Okay. So we are good to go. We are good to go, and let me start the session. So I'm going to talk today on cache-aided NOMA networks. And in cache-aided NOMA networks, we'll first talk a little bit about what is NOMA. Already you know a lot of NOMA, but that's why I will be brief. And then I will be talking about the cache, what is caching and how it can help the NOMA networks. And then I will be talking about some use cases or verticals which we can develop from cache-aided NOMA network concept. Particularly, I have taken three use cases, which are probably emerging areas. One is millimeter wave, the other one is mobile edge computing, and the third one is unmanned aerial vehicle, or more generally non-terrestrial networks. And then we'll spend a few minutes of time on standardization. As you can see that we are currently building an IEEE standard. So we have acquired some knowledge about standardization, and it's good that India is also taking actively part in standardization. So there is a big scope of NOMA standardization as well. So the structure of the talk is something like that. The whole session is divided into three parts. In the beginning, we'll be talking about cache-aided NOMA. And after cache-aided NOMA, we'll be talking about the verticals and use cases. And then we'll be talking about standardization. So let's start with the first session, which is cache-aided NOMA. Well, this is the first slide, which probably is technical in nature. And here we try to talk about the multiple access strategies. Well, first of all, let us just review what we mean by multiple access. By meaning multiple access is that whenever we consider any wireless solution, be it cellular, be it Wi-Fi, be it Bluetooth, or any other kind of wireless solution, most of the time we have multiple users sharing the same wireless channel. In a wired channel, the multiple access is much more easier because the logical divisioning sometimes can be done physically. What I mean is you can assign different pair of cables to different set of users, and automatically we can have a multiple access. However, in wireless channel, everybody can intercept every other signal, and that's why it is very difficult to make sure that everybody is using the same wireless channel and the signals are not getting mixed up. So from the beginning, the multiple access was a part of wireless channel transmission, where multiple transmitters and multiple receivers are involved. Apart from that, when we consider the frequency allocation, the multiple access is even more relevant. Why? Well, the mother nature has not given any restriction that we should use probably 5 to 6 gigahertz band for Wi-Fi, 2 to 3 gigahertz band for cellular or something like that. But we ourselves has restricted us to do so. The reason is that there are different kinds of services which all uses the same wireless channel. For example, your dish TV antenna, which is placed on your rooftop, is getting the signal from satellite, which is a wireless service. Then your mobile phone is getting a signal from the nearby tower, which is again another wireless service. And then probably you are working on your TV remote, which is again another kind of wireless service. Now, all these signals are present at the same time in the wireless medium. So not to jeopardize the services with each other, the regulatory bodies have assigned different frequency bands for different services. The defense sector has got its own chunk, the satellite service sectors has their own chunk, and the cellular service providers as well. Well, historically, the cellular service providers were not thought of going to make it big. What I mean is, when in 1980s we started cellular services, people thought that cellular service will be of will probably attract limited number of subscribers. So the regulatory bodies actually was not very keen to give a large chunk of spectrum to the cellular service providers. And the trend actually continued. The number of subscribers increased exponentially, but all the time the regulatory bodies failed to intercept the demand prior hand. And it's a common story in the cellular domain that the available spectrum is always far less than the demand is. So there was always a need of grouping different users on the same channel. Now, when you are grouping a number of users on the same channel, you have to make sure that this signals does not get mixed up. So you can use different verticals or axes for realizing. So when we consider the 1G, the first generation of mobile communication system, which appeared in late 80s and early 90s, examples like AMPS, which was in US, or TAX, which was in UK, or NMT, which was in Scandinavian countries. AMP stands for Advanced Mobile Phone System.
Excuse me, sir.
Yes.
Excuse me, sir. Sorry to disturb you. Sir, for me only first slide is visible.
Okay,
Just
I don't know.
check. Sir, any feedback from the participants?
Yes, now it is on a third slide, sir.
Okay, yes, yes.
Yes, sir. Now it's
Okay, I think
moving.
the problem is with the full
Slides
screen.
only.
Thank you, thank you.
Okay,
So I'll
thank you.
continue on this mode where probably you can see all the slides. Okay, so I'll just, this is the first slide, so we have not missed anything. So I'll just start again. In this slide, you can see there are 4 different multiple access strategies: FDMA, TDMA, CDMA, and OFDMA. And they are related to different cellular generation standards: 1G, 2G, 3G, and 4G. So let me talk about once again the multiple access strategies and their reason why they have been so crucial. The multiple access strategies were always required to feed multiple users on the same wireless channel, and it depends on which resource you are using, either the frequency or the time or the code or probably time frequency jointly. That gives rise to different type of multiple access strategies. Let us go back in the history in the the late 80s and the early 90s, when we had AMPS, Advanced Mobile Phone Systems, in US, TAX, Total Access Communication System, in UK, or NMT, Nordic Mobile Telephone System, in Scandinavian countries. Well, at that time, the services were not digital. So the only domain that could probably be used to group multiple signals together was frequency. So the whole frequency band was divided into sub bands, and each band was allocated to a user. So this was how FDMA came into picture. FDMA stands for Frequency Division Multiple Access, and that was the primary multiple access strategies for 1G. Now, in middle of 90s, to be precise, in 1995, GSM hit the market, and 1994 was the time where CDMA was introduced, or rather, DAMPS was introduced. I will be talking about CDMA later. So the DAMPS and the digital amps and the GSM, which all had this digital capability, well, at that time, there was a new domain, which was time domain. Now, time domain can be multiplexed as well, and the signals could be grouped in the time domain. So TDMA came into picture, which is time division multiple access. Now, in the late 90s and in the early 2000s, we had something like 3G. Actually, in 2G, there had been already CDMA standard evolving, and there had been a long tussle between the European group and the US group, GSM versus CDMA. And if you remember your early mobile phones, then we had this tussle. Like some people, some of us, we had Airtel and BSNL. Some of us, we had Tata Indicom and so on. So India was probably one of the few countries who enjoyed both these groups' advancements. But somehow people thought that this war should end and we should converge into a common 3G standard. So when 3G UMTS came, a universal mobile telephone system, then people embrace CDMA. Now, in CDMA, what we do was something interesting. Here, we use the whole time and frequency blocks, but we separated the users on the code domain. So each user was assigned a pseudo noise-like code, and in the receiver side, that code was used to separate the signals. Now, in 4G, the thing has emerged a bit further, and we moved from CDMA to OFDM, which is orthogonal frequency division multiplexing, where we have used jointly the time frequency blocks, and we realized the multiple access in this way. So this is the journey of the multiple access throughout the generations, 1G, 2G, 3G, and 4G. And currently, we are in the 5G era. 5G has been picked up by many of the countries. If you want to know the status of 5G, well, we expected 5G to roll out faster, but the pandemic and other business decisions around the globe slowed down its introduction. However, as of now, there had been at least 40 countries who has got their 5G networks, and around 200 of network operators has already started 5G operations. In India, the 5G is in the test phase. The TRAI, that is Telecom Regulatory Authority of India, and DOT, Department of Telecommunication, is jointly monitoring this, and we probably are going to have our own 5G network soon. Last week only, I have got some news from TSDSI, which is Telecom Standards Development Society of India, and they have collaborated with 3GPP, which is the third generation partnership project, and they have officially gave our 5GI, which is 5G in India, which is one big step in Make in India group. The 5GI standard has been already incorporated in 3GPP. So very soon, probably we will be having our own 5G standard, which is 5GI. I stands for India. That's a big thing. Now, what are the multiple access strategies for this 5G network? And probably in 2030 or so, we are going to have 6G. So what we are thinking about the multiple access strategies for 5G, beyond 5G, and in 6G. So that's about in the next slide. Well, in the next slide, I again draw the TDMA, FDMA, and CDMA, where we have shown the time domain, frequency domain, and we have included one new domain, which is called power domain. Now, the first picture on the top left is TDMA, which is 1G. Then the second is FDMA, which is in 2G. CDMA is on the top right corner, which was used in 3G. And then WaveDMA, which was the case for 4G. Now, NOMA is one of the big candidates for 5G. Well, you have to understand that whenever we talk about any generation like 3G, 4G or something, that runs for entire decade. So it is not the case that the whole standard is available at the beginning of the decade and it continues without change for 10 years. Rather, it's a very slow, gradual, but continuously changing process. So over these 10 years, starting from 2020 and going up to 2030, we will be seeing different revolutions of 5G, and we will be seeing different modifications, alternations, additions. So it's like a very gradual process, and by the end of 2030, we will be probably reaching 6G, where 5G has been modified a lot, and probably we can say that it is now turned to a new generation. Now, NOMA is one of the candidates which has not been yet incorporated in one of the standards, but it's a very strong candidate where we are not only considering any time or frequency resource block to separate the users. Rather, we are using the whole time and frequency block for all the users, but we are separating the user signals on the power domain. Well, that is somehow a truncated vision of NOMA, because you can also consider CDMA as NOMA as well. But more on this later on. First of all, let us answer a very simple question: why NOMA? Well, when we are talking about NOMA, we should understand what is OMA, like when the N is absent. Well, if you consider OMA is orthogonal multiple access. What is orthogonal multiple access? In orthogonal multiple access, we use either the time or the frequency or jointly the time frequency resource blocks to separate the users. So that means if you have, say, a frequency band which can support 10 users, then you can subdivide the frequency band into 10 subbands and you can go up to only 10 users. Similarly, in the time domain also, you can only support as many users as it is possible with the data rate and the switching rate of your equipments. So once the slots, either the time slots or the frequency slots, are exhausted in OMA schemes, then you cannot accommodate any new user. Well, that problem was somehow satisfied or overcome in CDMA, where although we could use different number of time slots or frequency slots, but we can use different codes as well. And as long as the codes are orthogonal to each other, we can increase the number of users. So NOMA is also a similar, having a similar principle, which is different from OMA. In OMA, the number of simultaneous users are always limited, but in NOMA, you can always have some add-ons, like you can put some additional users by varying them in a non-orthogonal manner. So they are not separated in a non-orthogonal manner. So the separation is challenging. It is not easy or automated like TDM or FDMA. In TDM or FDMA, actually you don't need any iterative procedure. You simply have slots and you look for the slots. So the separation of signals is quite simple. But in NOMA, the separation of the signals are quite complex because the resource blocks are non-orthogonal to each other. But the advantage of NOMA is that you can put some more users. So the OMA schemes are probably not sufficient to support the massive connectivity for the 5G and their diverse quality of service. So what we mean by this statement, massive connectivity and diverse quality of service. Well, in 5G, one of the use cases is MMTC or massive machine type communication. We have seen that for last 10 years or so, not only our cellular phones are connected, but there had been a rise of various IoT devices, Internet of Technology devices, Internet of Things devices, where we can have now a smartwatch, we can have smart refrigerators, smart microwave oven, smart washing machine. Probably some people are thinking about smart shopper's bag and so on, whatnot, smart clothes. So whenever something is smart, that means it has some communication capability. And whenever it has some communication capability, probably you want to put it on cloud via internet. And when that is the case, the number of nodes which are communicating is going beyond bounds. Now, when the number of nodes are massive, then obviously the orthogonal multiple access schemes are probably not sufficient. You have to always look for some additional domains to play so that you can support always more number of users. The other thing is diverse QoS. Well, not all the users are going to have the same kind of data rate or same kind of latency or same kind of throughput. If you are playing an online video game, probably you need a huge amount of bandwidth. But when you are probably monitoring the outside temperature, your IoT device is probably only going to get energized once in an hour, and probably it will send a very short packet and then it will go on sleep mode. So when you consider a gaming machine compared to a temperature sensor outside your home, they have different quality of service requirements. And then when you consider autonomous driving, for example, then you have again another short packet but very high latency requirements. So you have diverse quality of service requirements for different services. And NOMA is one possible technique to support that. NOMA is no magic pill which will solve all the problems, but it is one of the candidates which you can probably think of in coordination with other technologies, of course, like MIMO and so on, which will probably give you an additional field to play. So I will just show you two graphs here to support what I was talking about in terms of numerical quantities. Well, these two graphs have been taken from the survey paper by Wai Liu et al., which appeared 4 years back in Proceedings of IEEE, which is the highest read journal from IEEE domain and having the highest impact factor as well. Anyway, so in these two graphs on the left hand side, I show you that how the NOMA is behaving in with respect to OMA. Well, you can see that when you are having a fixed rate of bits per second per hertz per user, then the average sum rate, that means what is the overall throughput for all the users, is much more higher. So on the left hand side, you can see the curves where the red lines are obviously by far it is superior to the blue lines. On the right hand side, I present again another curve from the same paper where we compare the outage probability versus SNR. So what is outage probability? Well, if you consider the wireless nature of the channel, then
Sir, please share the full screen.
Actually, when we share the full screen, I'll try to maximize it. But when I'm trying to share the full screen, unfortunately, the slides gets freezed. So that's why the problem is. Okay, I'll try once again. See, can you see the full screen now?
Yes, sir. Now it is clear.
Okay.
Thank you, sir.
So if I change it, does the slide changes in your place? So can you see slide number 6 now?
No, sir.
So that's the problem actually. So
Sir, you can highlight this particular slide. Just click on the screen and then try to change.
okay. So maybe
This particular screen presentation should be on.
yes. So can you see the slide number 6 now?
No.
I don't know. So I tried all the possibilities.
Now your pointer is there. Now just see sir, now changing. It is changing.
Okay.
Control focus, our computer focus should be there. This particular process should be on. Then it allow you to modify.
Okay. So I think now you can see slide 5 and now you can see slide 6.
Yes, sir.
Okay, great. So I got it. Well, actually, thank you. So what I was talking about is that I was talking about the right-hand side graph. So where I compare the outage probability versus SNR. So what is outage probability? Well, the outage probability is when you consider a wireless link. The wireless link is often in outage or there is no connection between transmitter and receiver. That situation is known as outage. Now, the outage occurs due to the random fading, which is due to the perturbations in the channel, which can be due to many different factors. Now, obviously, the outage probability gives you an idea about how good a quality of the link is, and we always want to improve the outage probability performance of a link. Now, on the right-hand side, we show 3 curves. One is OMA, which is the blue line. Then the red line, which is non-cooperative NOMA, and then the cooperative NOMA. And you can see that obviously with signal to noise ratio, the outage probability goes down because when the signal is more powerful than noise, then outages are less. But you can see that for a given SNR, suppose at 30 dB SNR, you can see that the outage with cooperative NOMA is something like at least almost 1 order low compared to the NOMA, the OMA case. So these 2 graphs collectively show why the NOMA is far more superior than OMA cases. Okay, so next we'll talk a little bit about the NOMA thing. Well, here I talk about the 2 major classes of NOMA. The first class of NOMA is PD NOMA, which is power domain NOMA. And the second NOMA is called CD NOMA or code domain NOMA. Well, the code domain NOMA is almost well known because it is something similar to CDMA or code division multiple access, which probably you have gone through at multiple avenues where we can use different pseudo-noise kind of sequences. So I will not be focusing much on CD NOMA. Rather, we will talk about PD NOMA, which is somehow a relatively new concept. Well, the inherent concepts are not very new, but the combination is something new. So when we see the PD NOMA, it is basically a combination of 2 techniques. The one technique is applied at the transmitter, which is shown as TX. The other technique that is applied at receiver, which is shown as RX. So for realizing a PD NOMA or power domain NOMA, what we do is we do a superposition coding at the transmitter and we do successive interference cancellation at the receiver. Now, what does this mean? Well, first of all, what is power domain NOMA? In power domain NOMA, we separate or try to separate the signals in the power domain. That means different users will be given different amount of power or average power to transfer their signal, either in the uplink or in the downlink. Actually, in the downlink, they are different in power domain, but in the uplink, they will be inherently different in the power domain because they will be at different distances. Now, when this happens, well, of course, suppose there are only 2 users and 2 users are transmitting at 2 different power levels, but they are using the same frequency, they are using the same time, so their signals get mixed up. So how do the signals are combined and at the transmitter and how the signals are separated at the receiver? Well, the answer to the first question, that how the signals are combined at the transmitter, is in the superposition coding, where we generally encode the poor channel. Poor channel means the channel which is having a higher fading or less amount or more path loss or something. Then we encode the signal at a lower rate, and then probably the other signal is encoded at a higher rate, and then we add. That is superposition coding at the transmitter. On the other hand, in the receiver side, the thing is much more complex, where we do successive interference cancellation. So what it means? Well, a receiver receives both the signals, meant for it and meant for another user. So how it separates the signals? Well, first of all, it tries to decode the strongest signal. So it may be intended for it or it may not be. But what it does is it goes on detecting the strong signal and then re-encode and remodulate the signal and then subtract it from the composite signal. So it's like signal 1 plus signal 2 is coming to you and both are modulated. So you try to figure out what is inside signal 1 first and then you remodulate and then you get a clean copy of signal 2 because you are subtracting signal 1 plus signal 2 minus signal 1. So you get signal 2 and then you detect the second signal. And if there are multiple signals, you go on, repeat this scenario. So that is known as successive interference cancellation. When you do such kind of thing, we have something like this. So on the left hand side, I show sorry. Oh, I'm sorry. I have gone few slides back. Okay, so I think now you can see slide number 7. Well, in slide number 7, what I try to show is on the left hand side in figure A, it's again taken from the YLU paper, which it's very nicely demonstrated there how we can work with NOMA. Well, suppose there are two users, user M and user N. And in user M, we have allocated a large amount of power. For user N, we have allocated at a small amount of power. Now the uplink and downlink, well, what is uplink and what is downlink? Uplink is from the user to the tower. Generally, you have to look upward to see the tower, so that's why it is uplink. Downlink is from tower to your mobile, so it's downlink. So let us talk about downlink first. Well, in downlink, what we do is we use different powers and then we send the same signal to user N and user M. So both of them get the signals. Now, user N, what it does, it first, let us talk about user N. User N goes for a successive interference cancellation. How? Now, user N knows that user M signal is always there. So it first detects the strongest signal, which is user M, and it subtracts the user M signal. So what is left is user N signal. Now, suppose there is if there is no cooperation, then user M also goes for direct detection. But if there is some cooperation, the dotted line, then the user N can send the information to user M. So user M need not to have the detection. On the other hand, if you go for uplink NOMA, well, in uplink NOMA, actually you don't need to separate the powers in such a case because the users are at a different distance. So ultimately their power will be imbalanced. Now it will take help of this power imbalance. In the base station, it will go for successive interference cancellation, and here it will start with user N detection, and then once it is detecting the N detection, it will subtract and then you will go for user M. So in this case, it will again go for the nearest user, which is probably the stronger one, and then it will go for the user M detection. So this is how the NOMA is being realized in both uplink and downlink. And after we have discussed NOMA, let us talk a little bit of caching. Well, I hope you have heard about the term cache. Cache memory is probably when you buy a computer, you look for how much cache is there. L1 cache, L2 cache, L3 cache, and so on. Then probably in a mobile phone, you also look for cache memory. So probably you know a little bit about what a cache memory is. If not, let us refresh. Well, in an ALU architecture or in a CPU architecture, you have a cache memory which can store the repeatedly used instructions. So it can help the processor to get the thing faster, because when you try to extract the instructions or the data from the main memory, turnaround time is slow because you have to search a lot. So if you can store some of the repeatedly used instructions or repeatedly used data in a more convenient small location, then the whole process is faster. So that is cache. So that cache idea is relevant, very much relevant in network as well. What we do in network, Well, if you do not think about NOMA, let us forget NOMA for a time being and let us just think about the internet. Well, think of a viral video. You are looking at a viral video and your friend is also looking at a viral video and everybody is probably in your localities looking over it from YouTube several times. Well, you know that the YouTube main server is in US. So every time if you want to look at the video and every time if the video has to be delivered all the way from US to India, then it's not a very good network design thing. So probably YouTube has got its own server in India as well, and probably a copy of that video is stored in the server in India. Now suppose it is only popular in one state. Now we are talking to people who are probably, most of the people are from Rajasthan. So probably a video of local content is popular in Rajasthan. So it is probably more intelligent to put a copy of that video somewhere in Jaipur or in Jodhpur or somewhere else so that the fetch time is minimal. So this is how the cache is always there in network design. In every gateway node or every node that your network traffic goes through, it has got some memory where the most popular files, the most used things are generally locally stored. And obviously it has a time to die. That means the memory is obviously not of infinite capacity. So the new things come up, which are like every 2 days you have a new viral video. So the new viral video goes in, the old viral videos go out of the cache. And now if you want to see the viral video once again, which was popular 2 months or 3 months back, then probably it will take some time. It will not load as fast as probably the current viral videos because the cache is not storing it anymore. Okay, so that is to give you an idea of cache, what cache is, what cache memory is, and what cache memory can do in networking. Now, while you are doing caching, you have two phases. One is the content placement phase and one is the content delivery phase. That means the cache memory in your nearby gateway, which can be your mobile base station also, is going to attract some content and it will be placed in that cache memory. And then when the user demands, the memory content should be delivered to the user. So there are two phases. One is placement or collecting the cache contents, and the second one is delivering the cache contents. Now, during the content placement phase, what we generally do is we generally store the network during the off-peak time, like while we are all sleeping, like in the night time, probably the network is not busy carrying user data. So at that time, the network probably can refresh its cache memory through the backhaul links from the core network. So the idea is like there is a big core network and then there are some base stations connected to it via backhaul link, and those base stations are connected to the users via wireless link. So during the daytime, probably you're making a lot of calls and so on. So that time the backhaul links, the core network is very busy in transmitting the actual user data on real time. But in the night time or during the off-peak time, probably the base stations can access or refresh their cache content. And then in the daytime or somehow the network obviously sharp the cache contents. Now both these phases can only work well when you have an efficient cache placement strategy and cache delivery strategy. Then only you can probably get the maximum benefit out of it. Okay, so here I try to show, this is actually a figure from our paper which we are going to submit to IEEE Communication Service and Tutorials, which is on the cache-aided NOMA networks, where we try to show different caching techniques and cache networks. Well, in this figure we show five cases where on the A, this is A. Here we try to show D2D or device-to-device caching, and then here we show multi-hop relay. Here we show cooperative D2D. Here we show the edge caching techniques. You can see this green cylinder as a cache. And then in E, we show cooperative edge caching techniques. So these base stations also cooperate among themselves and probably share the cache contents. So suppose the user here, this user here is going in this direction, so the mobility can be predicted, and this cache content can be probably provided here, so that the user can probably still continue to enjoy whatever content the user is now downloading without referring to the backhaul link. So you can see inside we have an internet server which is the cloud, and these lines are backhaul links. So and these backhaul links are heavily used. So we try to reduce the use of such backhaul links. So this is how we do this. Well, this user is probably getting something from the base station, and if that thing is already available in the cache, it can readily give it to this person without going all the way back here. So the idea is this person wants a file right from here, but this file is already stored in the cache, so probably the local communication is sufficient. Again, when this person is going in this direction and probably going for a handoff, and probably is not going to be under this base station, is going to be under this base station. If you have some cooperation between these base stations, then this cache content can be updated here. So when this person comes here, it can again enjoy the local communication instead of going back to the core network. So this is how cache-based content delivery is done. Now, the most important thing, or the crux of this today's lecture, that is how this cache is probably going to aid a NOMA network, or NOMA is going to aid the cache in either way. Well, again, this is another picture from our Again, this is another picture from our paper where we are showing a base station with cache and several users. And suppose now the connection between the user and the base station is through NOMA. Now let us try to understand how this whole NOMA and cache can boost each other's performance. Well, when the information is available through caching, then we can probably go without the SIC. So to understand this, we go a few steps back again. We go here. So what was successive interference cancellation? Successive interference cancellation was you get multiple signals together, and then you subtract the strongest signal, and then remodulate it, and then you detect the first signal, remodulate it, subtract it, and then you go for the second signal subtraction. So it's something like you have two signals, you go for the detection of the other user signal, subtract it, and then you can get your own signal. So this is what is without cache. But suppose this user N has already got a copy of user M signal, which is also available in the cache. Then,
Sir?
Yes.
Sir, slides are not moving.
Okay.
Slide number 7 is visible.
Yes, I'm talking about slide number 7 only.
Okay. Sorry.
It's okay. So I was talking about cache-aided NOMA networks. That's why I have referred back to this slide. The idea is, suppose user N is trying to decode the signal, and without this situation is without cache. Now suppose the cache in the BS stores the user M signal. For in this case, the user N does not have to go for this step. So this dotted step is now removed. We can avoid the successive interference cancellation because we already have a copy. So we can directly go for subtracting of user M signal, and then you can get the user detection. So that is the idea of this cache-aided NOMA. So the cache-aided NOMA says that when the information is available through caching, then without applying the successive interference cancellation, user 2 can remove the signal intended for user 1, and it can decode the own signal. So that's the idea of cache-aided NOMA. And here I just go again from full screen to the this mode again. So here I will just show you that how the rest of the slides are. Okay, so we are at 10:13. So I think we are almost at the middle of our presentation. So I will just pause here for 1 minute or so, and I will ask the users if you have some queries, some issues, anything related to the discussions that was held now, or can we move forward? So if there is any queries, any issues, anything that we need to revisit, then we can do it now. Because we are almost at the midway, I think. Okay. Also, I think we have a chat box in MS Teams somewhere.
Box is not working, but
Okay.
unmute himself.
Okay. So the participants can unmute and they can also ask me if there has some issues. Okay, thank you. So
Hello, sir. Good morning.
yes.
Yes, sir. Actually, we have discussed about the interference cancellation. So we know about the process, but I just wanted to know particular SIC chatbot. Actually, SIC is a journey, but is there any kind of techniques which name are popular?
If actually your voice was cracking a lot, but what I heard intermittently was that you were talking about different types of SIC. Is it the case?
Yes, sir.
Okay, so actually, again, I have to tell you that SIC is nothing much new. It's a kind of an old technique, and the names were somehow different in the literature earlier. So I hope if you start with MUD, that is multi-user detection, then probably it will be easier to understand the journey. So we had earlier something called multi-user detection, which was proposed by Verdu and so on, probably 20 years, 25 years back. And that MUD was something like also used in maximum likelihood sequence estimation and other kind of things, like when we have this kind of trellis based detection and so on, and sequence based detections, they are all coming from the same concept of multi-user detection. So detecting multiple users simultaneously. The only thing that probably is remarkably different in SIC, which we discuss nowadays, is that SIC mostly is a single observation technique. What I mean is, in multiple user detection, generally the process is kind of long and probably iterative. Sorry, not only iterative, it is kind of having a kind of loop. But in SIC, it's a single observation thing, and once we cancel out one particular signal, then we never look back into it. So even if there are some errors or something, then we never go back for it. Now, how you optimize it obviously depends on different algorithms. Like you can go for some minimum mean square or LMS or something like that. So there are always certain algorithms which you can apply. So if you are aware about the equalization algorithms, so some of them are quite good for the SIC as well. So there are, and as I said, that these are only kind of, I should say, proposed. So we don't have a standard technique yet for SIC, but there are kind of like case-to-case basis SIC techniques. Like if, and it heavily depends on the superposition as well. If your superposition is a very simple power domain, then probably you can go for the cancellation just as I said. But however, if your encoding is complex, like different data rate, then it can be a bit difficult as well. I will show you one SIC technique that is going to be used probably in Wi-Fi 7. At least it has been proposed. So that will give you an idea how SIC works for a particular case. But as I said, that there exist different case-to-case basis, so I cannot name all the series. So I will just give you one example. Hope it will give you some idea. So please wait for a few more slides. When I will go to the standardization block, then I will discuss it. Is that okay? Okay, I hope so. So okay, so next is okay. So I will again go back to the full slide mode, and then if you have any queries, you can always ask me and always interrupt me at any time. So I will again go back to the full slide mode, and we are entering into the second part of our discussion, where we are going to talk about verticals or use cases. So what is verticals or use cases? Well, we gave you the basic idea of NOMA, we gave you the basic idea of caching, and then we have probably the basic idea of cache-aided NOMA, like when the cache is helping NOMA or NOMA is helping cache. Either way, you can say so. Now, how this cache-aided NOMA can be integrated into different new use cases or new verticals? Well, earlier we only used to think in terms of cellular mobile communication. We only thought about a mobile phone and a tower, or probably maximum Wi-Fi. But now with 5G and probably with 6G coming in few years, there will be multiple new use cases. And these use cases were not earlier present. So how this cache-aided NOMA is relevant in these new use cases is the next topic, where I will first, this is the first slide where I show you a few such use cases. There are a lot of such use cases, but these are some few use cases which we consider for our paper as well. Well, the first thing I want to talk about is NTN. Now, what is NTN? Well, NTN stands for non-terrestrial network. So what is a terrestrial network? A terrestrial network is what you see in the form of cellular communication. You have a tower on ground, you have another mobile which is being held by a person who is also standing on the ground. So a few feet above ground, probably the person, and a few tens of feet above the ground for the tower. But still, it is almost on the land, so it is terrestrial. But we have a new use case which is non-terrestrial. Well, is the concept completely new? No. Because satellites were always there. Satellites are not terrestrial, so they are non-terrestrial networks. But earlier, the satellites were very few. So the network design, operation, everything was not very complex. But now, not only satellites, but there are different unmanned aerial vehicles or UAVs that are coming into picture. You might be knowing about Google's Loon project, which is now shut down, but Google thought about blowing up balloons and providing internet access over remote areas in Australia, in some areas of Africa, and even in some desert areas in US as well. Now, although the initial boom of the balloon project is now doomed, but the companies are coming up with new exciting ideas. Like Facebook has got a project called Aquila, where they are providing high altitude drones. They are almost like aircrafts, and they are probably capable of providing internet access. Then there are low Earth orbit satellites, and some companies are pushing a lot of satellites into the space. For example, there is Amazon Web Service or AWS that is backed by Amazon, and Amazon has already got a lot of satellites on the space, and their close competitor is some other companies, including obviously the Elon Musk backed companies. So what I mean is the space is the next frontier for these use cases, where we are going to have a lot of non-terrestrial networks in the future. We will have drones, we will have low Earth orbit satellites, and then we will have something called CubeSats, which are somehow in between. Like you have satellites at the outside of the atmosphere, you have drones and balloons and these things or unmanned aerial vehicles in the troposphere, and then in between somewhere there can be some small satellites or CubeSats as well. So all these CubeSat, this unmanned aerial vehicle, the satellites, all together, they consist of non-terrestrial network. Then there is another domain called MMW or millimeter wave. Well, millimeter wave is a new band, not a new band, I should say, probably a new band to ponder over for wireless services, which were earlier useful only for satellite. So earlier, we only had up to 6 gigahertz of band for cellular communication. We never thought about like 30 gigahertz, 60 gigahertz kind of thing. But with millimeter wave, we are thinking about so. And this band provides you a huge bandwidth. So if you want tens of GBps of data rate, you can do it. Well, if you remember Shannon's basic data rate law or capacity law, you know that C is equal to B log 2 1 plus S by N, right? So when the bandwidth is more, then the data rate is obviously going to be more. So millimeter wave is going to promise us a huge amount of data rate, and that will be crucial for applications such as virtual reality, augmented reality, holography, autonomous driving, and so on. Then IoT, probably everybody knows about IoT. I have already interacted with one participant. I have seen that you have already got a lot of background knowledge. That's very interesting. So I don't think I have to talk about IoT, but I just, for the sake of completeness, IoT stands for Internet of Things. So already I talked about that next generation devices are going to be all having communication, computing, and internet capability. So they are going to be IoT devices. Then V2X, well, that is one of my area of work, where V2X stands for vehicle to everything. So we can have vehicle to vehicle, vehicle to infrastructure, vehicle to home, vehicle to grid, vehicle to pedestrian, vehicle to bicyclist, and whatnot. So next generation vehicles are going to be a powerhouse of computing and communication capabilities, and they are going to communicate a lot. So these are going to be new aspects of communication as well. And finally, MEC, which is mobile edge computing, where we are taking the tasks offloaded from the cloud and putting into the edge, and probably we help them to probably offload the task and do it in a distributed manner. So in this section, I'll be talking about 3 use cases because I cannot talk about all. So I've just chosen 3: the NTN, the MEC, and MMW. We have excluded the V2X and IoT. So this is the first use case or vertical where I'm talking about non-terrestrial network. So on the left hand side, I show a particular use case. Suppose there is a base station near a stadium. Now, when there is no match, suppose it's a football stadium and you have a football match, and when there is no football match, obviously the number of users in that area is very low. But suppose there is a high voltage football match between Real Madrid and Barcelona, for example, and then obviously the whole ground is filled up. People are using their mobiles, and not only that, they are taking the videos, they are sending it in real time, they are watching the live feed, and so on. So there's a huge amount of requirement of communication. Now, this base station may not be able to probably fulfill all the demand. So what is a popular new generation thing is probably you provide an UAV or unmanned aerial vehicle, which probably will flow during the match over the stadium, and probably it will act as a local base station or a relay for the base station. And with this, if it has its own cache as well, then it will be much more useful. So because you see, when you are watching on a Real Madrid versus Barcelona match, probably you are going to download again and again the same match highlights, or probably during the break you are looking at the old matches of Barcelona or Real Madrid. So the contents are very similar, what probably they are requesting, or probably some weather services, or probably some map services near the stadium, how you can go back to your home, or how you probably catch a bus to another city. So all this information probably can be put in the cache, and then it will be much more useful. And if you use NOMA, then probably many more users compared to the available slots can be accommodated. So on the right hand side, I show you the phases of such kind of vertical. Well, first of all, you do the deployment, like you have a base station and you put an unmanned aerial vehicle. Here we show a aeroplane shaped drone, but it can be of any shape. So the first step is deployment, and obviously the content placement. So you obviously put some material into the cache, like the last match of Barcelona and the last match of Real Madrid, which is already put in the cache, the highlights, the team settings, and so on, which are probably popular. Then in the when the content is placed, well, of course, when the match begins, the users starting to request the contents. Now, when the requests are coming to the drone or the local base station, if it is already having the content in the cache, it goes for the content delivery direct to the user. But if it is not there, then it asks the base station, and the content request is directly going to the base station, and then there is a content delivery. So of course, everything you cannot put in the cache, so there will be something directly going to the macro base station. But if you can do this, then you can reduce a lot of load on the base station, because most of the local communication can take place through the drone and not going back all the way back to the network. Well, the next use case is mobile edge computing. And in the mobile edge computing, we are showing here a cloud and internet server, and these are backhaul links, of course, and these are base stations, and these are the file transfer request. And here we have different kind of users: laptop, tablet, car, smartphone, and so on. And we have cache. The base stations are with cache and MEC server. Now, what we do in this case is, if you suppose are doing a cloud computation job. Now, this cloud computation job can go all the way back to the cloud. Now, if you have some cache here, then probably you can divide the task in these areas as well. So when you consider a cache-aided NOMA in mobile edge computing, you can offload the task from the cloud. So that's the idea. And finally, I show you the third use case, which is the millimeter wave, or some people are even talking about terahertz. So what is millimeter wave? Well, millimeter wave is the wave where the wavelength is of the order of millimeter. So if your frequency is such that your wavelength is between 1 millimeter to 10 millimeter, then your signal is millimeter wave. Roughly speaking, if your frequency is between 30 gigahertz to 300 gigahertz, then your signal is millimeter wave. However, above 100 gigahertz, signals are not generally considered in a millimeter wave, and they are now considered as a terahertz or sub-terahertz domain. Now, in the terahertz or millimeter wave or something, we have, as I said earlier, that you have a huge amount of bandwidth available. So you can accommodate a lot of data rate. But you have to consider certain interesting facts in millimeter wave. Well, in millimeter wave, the transmissions are not unidirectional anymore. What I mean to say is, when you consider a 3 gigahertz transmission, then the antenna can transmit the signal around it, at least on the azimuthal plane, in a uniform manner. But when you try to transmit the signal at, say, 30 gigahertz, then your transmissions is always within a cone. It's not going to satisfy users at all the azimuthal plane, all over the azimuthal plane. Why so? Well, this is due to the antenna design. Well, in the millimeter wave, the transmission is so directional that unless you make the antenna satisfying a particular cone, you cannot realize a sizable gain for the antenna. So the signal won't travel. In general, in millimeter wave, the signal does not travel much, because at higher frequencies, the absorption and the attenuation is higher. So the radius of the cell is less. But not only the smaller cell is an issue, but also the directional transmission is an issue. Now, these can be sometimes effective, sometimes it can be a challenge. Now, how cache-aided NOMA can come here? Well, if we consider NOMA-assisted millimeter wave, then we can increase the number of users further. But caching can also help, because it can offload the core network traffic. So here we actually show a picture. Unfortunately, I forgot to give the reference here. So it was from a communication communication magazine paper, IEEE communication magazine paper. So I forgot to give the reference here. Sorry. Anyway, so this is the macro BS, and we have.
Sorry, sir. Again, I'm disturbing. We are showing only at slide number 11.
Oh, that's why. I don't know. I tried this clicking and everything.
Now it's on slide number 15.
Okay. So fine. Thank you. So I will probably not go to the full screen mode. It's so challenging for me. Thank you. Okay. So the millimeter wave or terahertz, here I'm trying to show that we have a sub-6 gigahertz spectrum, and here what we see is that there is a millimeter wave base stations here, the small scale BSS, this, and then we have this millimeter wave spectrum which is within this band, but the sub-6 gigahertz spectrum can cover the overall area. Now here what we can do is, in the millimeter wave NOMA small cells, multiple users can be accommodating, but we can further increase the number of users when we consider the caching offload kind of thing. So I repeat again, because there are some issues with the slides, so I will repeat again the slides. So what we see that, well, we have some verticals or use cases. And in the vertical or use cases, there are 5 use cases. I talked about NTN, which is non-terrestrial network, which is about drones, satellites, the CubeSats, and so on. Then we talked about millimeter wave, which is the higher frequency range from 30 gigahertz to 300 gigahertz. Then IoT, all the smartwatch, smart sensor, and so on. Then V2X, this is between vehicle to pedestrian, bicyclist, other vehicles, infrastructure, roadside units, and so on. And finally, MEC, or mobile edge computing. So I'll just give a summary of what we discussed so far. Well, in a non-terrestrial network, what we do is we have a base station, and then we have a cache-aided UAV, which is going to serve. So when there's a match, we probably fly the drone at that time, and the drone is already equipped with a cache, which is probably storing the data for the previous match, and so on. So these are the steps. Well, first you deploy, that means first you run the drone above the ground, and you also put data in the cache, and then the users here start asking for the content, and if it is available in the cache, it rightly delivers. If not, it goes to the base station. So the idea is to reduce the communication between the user and the base station by providing a cache-aided thing. And with NOMA, we can increase the number of users which the drone can support, because it's very difficult for even a single drone to support many users altogether. So if you use NOMA, then you can increase. The second use case that we talked about was mobile edge computing, where we have some cloud or internet server, and then we have backhaul links and so on. And if you have the base stations with mobile edge computing servers and cache, then you can offload some tasks from the cloud. And finally, we talked about millimeter wave or terahertz, where we can have some overlay kind of concept. We can have a big area covered by a big base station, which is probably operating not in the millimeter wave, but in the sub-6 gigahertz spectrum. And then we can have small cells within that area where a lot of users are clustered. So these are the millimeter wave base stations. Now it can accommodate a lot of users, but if you use NOMA, you can increase the number of users further. And with the use of cache, then you can also reduce the traffic from the between the macro base station and the small scale base stations as well. Okay, so with this, we move to our third part of the presentation, which is standardization. Well, NOMA has been discussed at various fronts, and people were probably coming up with theoretical solutions as well as some of the practical solutions in some cases. But unless it is standardized, we are not going to see a product with a NOMA. So when we have some standardization, then only the companies build hardware on the basis of that, and then only you can get it in the market, and then probably it's widespread. So standardization is very important for any technology to thrive, to persist. Okay, so let us think of different domains where NOMA and cache-aided NOMA is getting standardized. First of all, we should stress on the fact that cache-aided NOMA is still a concept. So you won't find, as far as I know, a cache-aided NOMA or simple NOMA-based device for purchase over Amazon or Flipkart or eBay. So, but there had been some standardization activity. So that's something like a very promising thing, because once the standardization starts, we are going to expect products in the end. Well, if you consider the Wi-Fi domain, in the Wi-Fi domain, there is a, you know probably that Wi-Fi standards are 802.11 standards. 802.11b was actually Wi-Fi, and then 802.11a became WiMAX and so on. It was then 802.11g, n, ac, ad, and so on. Well, there is a group called AICTE study group, Extreme High Throughput Study Group. So they are talking about SOMA, which is something like semi-orthogonal multiple access, which is a kind of NOMA, and they have already got a prototype based on this. So that is available from this IEEE network paper. It's a group of Professor-HAG. He's from Georgia Tech, currently in Russia, who is pioneer behind such technologies. And let me briefly talk about here. I will just, one of the participants was very kind to ask about the successive interference cancellation. So here I try to talk about how this successive interference cancellation is generally realized. So what they are trying to do in this Wi-Fi standardization through NOMA is that, suppose you have two signals. Here we have this, and they are QPSK signals. So they are imposing two QPSK signals on one another with superposition coding. So how? Well, suppose you have this yellow signal, which is probably the stronger signal, and the red one, the B one, is probably the secondary frame. Now, when you go to picture number C, so when you see picture number A, that is the primary frame, picture number B is the secondary frame. So both shows QPSK constellations. And you have to add them together. So you have to go for some superposition coding, and in the receiver side, probably you have to separate them out. So how the superposition coding is being done in frame C, if you see that, well, you go for a stronger power for the primary frame, and then you go for a weaker power for the secondary frame. So overall, the constellation goes to the red dot. So it is going to the yellow dot, and then it's going to the red dot. Now, that is for without gray mapping. Now, if you go for gray mapping, then the frame number D shows where the position of the thing is. Now, so the top part is how the superposition coding is done. Now, let us try to see how we are trying to get the signal decoded, or successive interference cancellation or something like that. Now, in frame E, actually we see the NOMA frame that we receive with low noise level, of course. And in F, we see a case where there is a lot of noise. So the whole thing has shifted. And the red diamond is showing the decoder decision. And the cross signal is what we have received actually. So when we have got a lot of noise, then you can see that probably we are decoding something quite wrong. But when you see that we have got gray mapped NOMA frame, then we are within the red block or the pink block, and also at H frame, even with high noise level, we are still within the pink block. That means we are able to recover most of the bits correctly. So this is one such example how we do successive cancellations and successive removal of the thing jointly. But as I said, it is a case-to-case basis. Okay, so now we move on to something different, that is another kind of standardization, which probably is going to include NOMA. We are going to talk about DTV or digital TV. Now, digital TV we are also enjoying currently. We have almost got all the channel digitized. So what is analog versus digital? Well, we had earlier analog signals. Now we have digital TV signals. Probably you know about the differences, like it's having more sharper features and more resolution and so on. But there are a certain war of standards, like US uses some standard called ATSC, but rest of the world, including India, uses DVB-T. DVB stands for digital video broadcasting, and ATSC stands for advanced TV service. I went 2 slides back. Sorry. Okay, so in ATSC, what I was talking about, the American standard, American television standard. So in American television standard, what we see is that we have already got some NOMA incorporated. Well, what they are trying to do there is they are doing something called layered division multiplexing. So what is layered division multiplexing? Well, it is an implementation of PD NOMA. PD NOMA is power domain NOMA. And now in LDM, they have 2 layers. One is the lower layer and one is the upper layer. Now in the upper layer, they are actually, it's having high power, and they are using it for mobile terminals. That means if you are watching the TV from your mobile or tab. And the lower layer, they are encoding the same signal, but for fixed terminals at a lower power. So that is how they are doing. And in the figure, we actually show how the thing is being done. So in the upper layer and lower layer, they are so the transmitter, when you see the transmitter, the two signals are mapped. So this is the superposition coding. But in the receiver side, you can see that we are doing this regeneration and we are doing the subtraction. Now here there are two signals, so the subtraction is enough. When one of the participants said that successive interference cancellation, well, this is one of the example of SIC, but here there are only two signals. Well, the other thing is in DVB, NOMA has not been yet incorporated, but there have been some proposals to include DVB-S2X and DVB-T. Now, the most important thing, that is the cellular domain, which probably everybody is eager to know. Like, what is the situation with 3G, 4G, 5G, whether NOMA is going to be there, when NOMA is going to be there, what is the status, what people are thinking about, and so on. So, and most of this information are classified because only the standardization bodies and their included groups are having the knowledge. Well, we were a little bit fortunate because we had some interaction with some standardization bodies, so we could gather some information. But however, only the exact 3GP people probably can give you exactly what happened, what is happening there yesterday or tomorrow. Still, we try to gather as much information as we could gather. And here we show the roadmap of 3GPP. Well, what is 3GPP? 3GPP is third generation partnership project, which is guiding the standardization of cellular mobile since third generation. It's something like when in 2G, there were two big groups. One group was GSM, the other group was CDMA. The GSM group was probably engulfing the whole Europe and Africa. The CDMA group was US and Latin America. There was war, and then there was something like peace. So how the peace was achieved? Well, they formed a consortium called 3GPP, third generation partnership project, where they agreed, okay, we should probably end this war, we should have a common consensus, and that standard should be probably abided by everybody around the world. Otherwise, the manufacturers cannot make phones according to a common standard. The telecom operators cannot build the towers according to a standard. The software providers cannot provide software for the telcos, and so on. Now, the 3GPP since that time have been releasing different standards, and we are terming them as something like 4G and 5G and so on. So the release 13, which was and release 14, which was 4G LTE. LTE stands for long-term evolution. They included NOMA as a study item. So that was in the year 2016. Now, when we got release 14 at the end of 2016, the study item was converted into a work item. That means study item is something like it can be included. Work item is must be included. So it was very promising for NOMA because they included something like MUST, or multi-user superposition transmission, which is one kind of NOMA, which is something like grant-based downlink technique. Like you give grant and then you go for the downlink. But unfortunately, what happened after that is in release 15, when you consider the release 15, in release 15, there was no consensus because at the time there were also players from NB-IoT, narrowband IoT, and so on. So this was happening in 2017 when we are talking about 5G new radio. So 5G new radio phase 1 was the release 15 from 3GPP, and this 5G new radio, when it came up in the first phase, there was no consensus at all. So actually there was no discussion on NOMA. Again, in 5G NR phase 2, which happened during 2019, just before the pandemic hit, then the NOMA for new radio was included again for a study item, and it was grant-free uplink NOMA. So it was not grant-based downlink, it was grant-free uplink NOMA, which was included in the study item. So that was the news until 2019 end. Now, what happened from 2019 end was that the COVID hit. So the release 17, actually release 16 was slated for much earlier in 2019, but it was delayed till the second quarter of 2020. So in 2020 June, the release 16 came, and release 17 is being talked about till that time, and release 17 will come in 2022 third quarter. So we are currently in the release 17 working, in the 3GPP people are working on that, and the most of the information is classified, as I said, but still we have got some news about SOMA, REMA, SCMA. So these are like semi-orthogonal multiple access or rate adaptive constellation expansion or sparse code multiple access. These are something like they are being discussed for release 17. So we yet don't know whether there will be some inclusion of NOMA in release 17 or not. And release 18 will be slated after 2022. So probably people will think about 6G and so on from that time onwards. So release 18 onwards, what will happen, nobody knows. But we can expect that this duration, which is called 5G NR evolution, starting from 2020 mid, and now we are in that phase. So in that phase, probably NOMA will be included for 6G. So we have come to an end of our discussion. And in this slide, I would like to talk about the summary of what we discussed today and the key points and the takeaways from today's discussion. And then probably we can have a short question and answer discussion session if you like so. So there are 4 points as a takeaway that I want to discuss. The first thing is it is very important to discuss the difference between OMA and NOMA. OMA is orthogonal multiple access, NOMA is non-orthogonal multiple access. So what is the difference between them? Well, in OMA, you can't use the same time or frequency resource block for different users. So either the time or the frequency or both should be different for different user blocks. But in NOMA, NOMA is something like add-on. So you can use OMA. On top of that, you can use NOMA. Like you can accommodate some more users by differing them in the power domain also. Then the second point that we would like to discuss is that why NOMA is important. Well, NOMA can support some more amount of users and it can provide some user fairness. What is fairness? Well, if you want some users to give some preference with some high power, then the NOMA can serve that purpose. And obviously, when you use NOMA, then you are not using the bandwidth, but you are still accommodating more users. So it is much more spectrally efficient. So with NOMA and with cache, you can reduce the transmission latency, you can increase the user fairness, and you can have a more spectral efficiency. And the third point is about cache. Well, I have explained what is caching. Caching is about prefetching the popular contents and storing them near to the user. So how we are how and what is an issue we are going to do, but caching is very important because we are storing the popular contents at the network edge. And the final point, which is probably the summary of the whole discussion, is that when you go from OMA to NOMA and you also use cache, then they together reinforce each other. How? Well, you can probably realize an OMA network where you are transmitting at different slots, time slots or frequency slots, fine. Then you give some add-on, you go for NOMA. Now in NOMA, what we have is we are having some additional domain to play where we can push the content to the cache networks. So when we push some additional contents without violating the regular transmission, then our cache is updated. It's something like you are getting your regular signal, but on the background, some future signal which probably you are going to access is getting stored near the base station, to the base station near you in the cache through NOMA. So you are getting through OMA. NOMA is probably storing some additional things in the cache, and they together reinforce each other's technique. So this is how cache-aided NOMA networks is going to be useful in future generation. And as we have shown that the standardization and everything is going on or taking place, so we are quite like sure that cache-aided NOMA networks is going to be an integral part of 5G plus networks as well as 6G networks. So this is an idea whose time has already come, and there are a lot of research going on and around on this topic. So here actually I stop my discussion, and before leaving, I would like to thank the organizers as well as my institution. I would like to thank the organizers from the Poornima College of Engineering and Poornima Group of Colleges who has given me this opportunity to talk in front of such a learned audience. And there has been a huge audience and very supportive audience. Thank you. It would have been better probably if we can interact a bit more, but due to the time constraint, we could not. So, but it was altogether a very nice experience. I would also like to thank my institution for giving me this opportunity to have this lecture. And I would also like to thank ACRB, Science and Engineering Research Board, who is providing the infrastructure support. And this lecture is obviously a part of an initiative of their social scientific responsibility or SSR policy. So that's all from my side. If you want to contact me, this is my mail ID. And you can also get more information about our group's research and development through this web page. This web link directly connects to the institute profile. And if there are some questions or some queries, because we still have probably 5 minutes left, we can do so. Thank you. Thank you all.
Thank you, sir. Thank you very much, sir. We are very thankful, and it was a very nice session. And now I request to all the participants, if they have any query, kindly unmute your microphone and ask to sir directly.
So Anila madam, how's the cold there? Like I have read that it has gone down below 0.
Yes, sir. Morning is very cold in Jaipur nowadays. Weather is like very.
Actually, I have a colleague from Jaipur. She is from Shikhar. You probably knowing that area.
Yes, 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 sir.
So actually, we sit side by side, and she was telling that the fields have been frozen and all the lawns and everything, they're having ice, snow kind of thing. So she tells that please come visit my home. It's like Kulu Manali now.
Yes, sir. So that area is the most coldest region in the Rajasthan also. Sikar Fatehpur region is the most coldest region. So shall we, sir, wind up the session? So
Yes,
I
yes,
request
yes.
I request to all the participants, kindly switch on your camera for a group photograph.
So the scope is
Thank you, sir. Thank you, everyone.
Thank you, everyone. Next session will be at 11:30 a.m. Thank you all.